So here I wanted to talk about the indexing for a little bit. So for this circulant matrix C, the first column is from 0 to n minus 1. There are n elements. So what if I want to, I can index them from 1 to n, okay? So this is the first, this is second, all the way to the nth. Or you can also zero index them. So this is the 0th element, this is the first row, and this is the n minus 1th row. So let's do that. Let's actually zero index. Use zero indexing. Use zero indexing. So the 0th element of x is x0, n minus 1th element is x n minus 1. So what if we say what's the nth element? So in that case, what we will do, we will rotate back to the first position. So if we go one position after the n minus 1, what we're doing, we are actually rotating back to the first position. So that's actually x naught. There's another way we can work it out. So let's say we are trying to get the n plus mth element. All we have to do is to just subtract n from that number. So n plus m minus n is m. If that's still larger than n, then again subtract n. What we're doing is that we are taking a modulo operation. So we'll this is actually the xm. Okay, so this is the rotating indexing we will be using in this case. So that's why wn minus 1 is w0. Wn minus 1 is wn minus 1 is actually w is equal to lambda times w0, and w0 is actually wn. Okay, so for x conjugate, as this is left shifting the vector w, we can write k plus 1 equal to lambda wk. We can use this one or this one, anyone we can use. Let's use this one. And from another property of the eigenvalue and the eigenvectors here, we can write wk plus 1 k plus l lambda to the power l wk. Why have we used l here, k plus l? Because we are multiplying the S matrix L times with the vector w, and we know okay, we are writing these equations for this for S conjugate. So let's write down the eigenvector eigenvalue relation. So we are multiplying S conjugate L times with the vector w. So we are actually left shifting the w vector L times, because we are multiplying L times the S conjugate, and that's why there's k plus L. So from here we can easily see that if we put L equals to n, we will get k plus n lambda n wn. But what is k plus L plus n? Sorry, that's lambda k. But what is k plus n? I have told you, just subtract n. So if we subtract n from here, we'll get wk equal to lambda to the power n wk. That gives us lambda n equal to 1. So lambda to the power n equal to 1. That just means that the eigenvalues of the matrix S conjugate are the roots of 1, n roots of 1. So, and if you know about the roots of unity, from the roots of unity, if lambda n is equal to 1, then lambda is equal to e to the power j twice pi over n m, where m goes from 0 to n minus 1. So this is our eigenvalues. So from this equation we can find the eigenvectors using this equation. So let's write that here, equal to lambda wk. Now if we put wk equal to, k equal to 0, then w1 w0, okay. Then if you put k equal to 1, we will get this thing, but using w1 from the previous equation, we get this, and so on and so forth. So we will get wn equal to lambda n w0. But we don't need actually wn, because wn is equal to w0. So we can write wn minus 1 lambda to the power n minus 1 w0. Okay. Now we know that we can write w, the vector w. We can take w not common from all of the terms here. So w1 common, w not common. First element would be 1, because that's the w naught. Second would be w1, which is just lambda to the power w naught, which is just lambda. Third would be lambda square, then all the way to the lambda to the power n minus 1. But we know lambda is this quantity. Let's say that quantity as rho m. So we will get w naught 1 rho m square dot rho m n minus 1. Now we have found the eigenvector of the matrix S, and from our previous property we know that the circular matrix has the same eigenvector. So we will use that eigenvector as an eigenvector of the circular matrix C, and then we will try to find the eigenvalue of the circular matrix C.